Hi everybody, we will continue the treatment of Ising model and the many field approach. I will just remind you what we achieved so far and where are we standing. So it's Ising model, mean field approach. Now, we have solved exactly the free Ising model where we obtain the following result. For any given, also the total moment M was mu. In average, I goes from 1 to n over si's. Right? And we obtain that this guy equals to mu n hyperbolic tangents of beta mu h. So nothing really happened over here, and this was due to the form of the partition function, which was derived by us, and it was z was equal to a summation of all the states, of e to the power plus beta mu h, sum I goes from 1 to n over si. Okay? So this representation of the partition function led to this behavior of the magnetic moment, and there is absolutely nothing interesting with this magnetic that happens to this magnetic moment. Well, because there is no phase transition. Right? So the plot, if you plot this guy as a function of h, and this is m, say divided by n, it's what we expect for any paramagnetic behavior system. It goes like this, and it goes like that. Okay, now what we started to do is we try to solve the problem when there is interaction, and when I mean interaction, we have interaction term, which was minus 1/2 beta sum over I sum over j of Ri minus Rj Si as j. So when we include this interaction term, the problem is with the multiplication. We cannot do any factorization, so we don't know how to solve it. And in order to somehow make progress, we assumed, and this is what was called the mean field approach, we assume that any si, okay, is approximately, we can represent it as m minus si, and this m is the average moment for all different spins, okay, where we don't know what this m is, and we assume somehow that this term is small. So basically we're saying the following. This is the mean field approach. The mean field approach says, well, you have on average all the different spins have exactly the same value. This value is m. I don't know what this m is, but let's assume that there is some sort of m that is present in the system. Now I assume that there are fluctuations. Why? Because there are interactions between the different spins that I have inside the system. I assume that fluctuations are such that those guys are not too large. Okay, so this is the assumption. Afterwards we perform summation, etc., etc., etc. And the last thing that we have developed was the following form for the energy. So the energy was minus 1 over beta, right? No, the energy was, no, there is no beta over here, I'm sorry, we multiplied it afterwards. So it was minus j squared m squared multiplied by n. All right, so this is the term that we had. Right, I remember it correctly. We have a beta. Beta will come afterwards. Beta will come afterwards. Okay, so this is the term minus mu h plus j, and this is j tilde m multiplied by sum I goes from 1 to n of Si. So this is the energy that we developed using this approach of mean field, where we assumed some small fluctuations, that we neglected multiplications or squares of those guys, and eventually we reached this point over here.
So did they have j without the square in the first term?
Okay.
By the units.
Yeah. Yes. Now, I remind you what is j. What is j tilde? Or j tilde is a sum I over I of j ri minus, let's call it r1, for example. And that's it. Okay. So this is j. We pick one specific point, it doesn't really matter what point, and we compute the sum over all those guys, which are the summation of all the different coupling constants between all the different sides and the lattice. Okay. Now, what's interesting in this picture? There is no interactions. In what sense no interactions? All the interactions somehow are now described by this term over here, an additional constant term which we add to the energy. Okay? So our assumptions led us to the following representation of the Ising model with interaction. We say that the Ising model with interaction, or at least the energy, it's equivalent or can be approximated by the energy where there are no interactions, so just free Ising model, but you have to modify your external field a little bit. It's not just mu h as it was over here. Okay? It's not just mu h, it's mu h plus something. Okay? And we also need to add this additional term, which is a constant. And the problem is with this approach, so which is very nice, right? So everything now falls down into the representation of an free Ising model. The problem is, what is M? Okay. This is our problem. We don't know what M is, and we need to find it somehow. Okay, so how do we find it? It's not that you can say, well, let's assume that M is small, let's assume it's M is large. We need to find it in a self-consistent way, right? Using some general laws of physics. So what I suggest, what we do now, let's see what happens, or let's develop this guy a little bit. Okay? What I mean by develop, let's write the partition function. So the partition function z, okay, the partition function z is sum over all states of e to the power minus beta. And what we have here is j m squared n. I think there was a 1/2. There was 1/2 over here. 1/2, it came from this 1/2. Okay, so there was 1/2. 1/2 minus, and also we have minus mu h plus j, it's j tilde m. The sum I goes from 1 to n over Si. So if you look only on this part, okay, just concentrate on this part. So first of all, this guy, it's not dependent on the state at all, it's just some specific constant, so we can take it out. So we have e to the power minus, or it's going to be plus, beta, 1/2 beta, j tilde, m squared, n. Okay? And here we have a sum over all states, e to the power beta mu h plus j tilde small m, sum I goes from 1 to n over si. Now, we treated this guy when we treated the very simple free Ising model. And this is exactly a very simple free Ising model. We say what we said. So, oh, all of those, it's factorizable sum, right? So if for free Ising model, when j tilde was 0, okay, we wrote this as, so for j tilde equals 0, we know that a sum over all states, e to the power beta mu h multiplied by a sum of I goes from 1 to n over si, is just z1 to the power n, where z1 was 2 hyperbolic cosine of beta mu h. Okay? So this is what we've got for j equals 0, for the free Ising model. Now I'm asking you, if the only thing that we do is modify this h over here. So instead of mu h, we have mu h plus j tilde n. It's a constant. So it doesn't matter. Okay? So what I'm saying is, we have an effective field. All of this is some sort of an effective field. So if I'm treating this as an effective field, I can repeat this procedure over here of factorization, okay, where instead of beta multiplied by mu h, beta is going to multiply mu h plus j tilde n. Okay. So I'm saying that this z, not a free Ising model, so this z equals to what? Equals to e to 1/2 beta j tilde m squared m z1 to the power n. Okay. Now z1 we're treating not for j equals 0, but we factor it exactly as if j equals 0, and we have this effective field. So z1 is 2 hyperbolic cosine of beta mu h plus j tilde m. So in total, we can write down that our partition function z is what? Is e to the power 1/2 beta j tilde m squared n 2 cosine, hyperbolic cosine of beta mu h plus j tilde m, and all of this to the power n. Hooray, hooray! We done it, right? So every moment that we manage to calculate the partition function, the usual idea is we've finished, we've done. But this is not the case over here. Why it's not the case? We still, what was the problem when we described the energy? We had no idea what this m is. Okay? And this m sits in our relation, in our formula for the partition function. It sits over here, and it sits over there. So we have a general expression for the partition function. If we knew what m is, we could calculate the partition function. But this is like, we started with what? We started with the intention to calculate m. How we needed to calculate m? By some calculation of the partition function z. Okay? And we ended up, yes, we calculated the partition function z, but inside there is a known parameter or variable m. Okay? So we're still in some sort of a conundrum, and we don't really know what to do. Now, at such point, you need to use additional constraints, physical laws, something about your system. So, what is this something that we know that have to happen no matter what? So, we don't know what M is, right? So, it's again the same question, what is M? And I can say, what is M? I will ask this question again. But have I used all my knowledge about the system? So actually no. There are some specific laws that always have to be satisfied no matter what M is. Now if you remember, so one of those laws that we constantly repeating in this class, and you repeat this law in other classes as well. So if you define some sort of a potential, in this case a thermodynamic potential, the system would like to sit in a minimum of this potential. In a minimum with respect to what? In a minimal with respect to different parameters of the system. Okay? So M, it's a free parameter, we don't know what it is. What we do know, we know that if we will look on the free energy, plotted as a function of M, okay? And this free energy can be something, and can be an awful function, okay? But what we know, that if we know what the free energy is as a function of M, which is our free parameter, we know that the system would choose one specific point, the minimum of the free energy. Okay? So if you think about it as a hilly highway, okay, and this is your car, so we are saying the car is going to be stuck at the minimal point, at the lowest point of the values of this thermodynamic potential. Okay? This is the only thing, this has to happen. No, so this is a prescription to find M, right? So if we have the free energy as a function of M, we can choose M. So this is a self-consistent approach. You find the free energy as a function of the free parameter. You don't know what this free parameter is. How you decide what is my free parameter? You decide what is your free parameter by looking on the finding the minimal value of your free energy. And what is free energy? Do you remember what's free energy? What is F? Minus 1 over beta log of z. And z is this guy. So we know z as a function of m. Therefore we know f as a function of m. So the only thing that is left is to find what happens to f as a function of f. We find a minimum. Okay, so we have a function, and you used to explore the function since high school. You'll find the minimum of this function, and periphery will know what m is. Okay? So we assume that m is something, we use this mean field approach, we define what is the free energy, and then we look for the minimum of this free energy. Okay? So this is the idea. And this is part of larger theory that is called Ginsburg-Wandel theory that we won't discuss much, maybe a little bit later. Okay, so the goal is, great, let's find f, let's find this minima, and decide what m is. Okay, so it's something constructive that we have in our hand now. And it doesn't seem really hard to do. Okay. So what we have, I have a very high doubts about the plus or minus sign of this guy. Can you check what we developed yesterday? Was it a minus or what is a plus? So it was a plus, and then when I multiply it by minus beta, it's going to be minus?
Yes.
Okay. So everywhere it's going to be minus. Okay. Everything else was fine. Okay. So we are talking f is minus 1 over beta log of what we have inside. We have e to the power minus 1/2 beta j tilde m squared multiplied by n. And here we have 2 hyperbolic cosine of beta mu h plus j tilde m. All of this to the power n. And here we cross the log. Okay, so first of all, what we can do, we can take n outside of the logarithm. So we know that f equals to minus n divided by beta. And here we have a log of e to the power minus 1/2 beta j tilde m squared. And we have plus a log of 2 hyperbolic cosine of beta mu h plus j tilde m. Close the parentheses, we close another parenthesis, close another parenthesis, and we close another parenthesis. Okay, so let's divide, let's declare that small f, it's capital F divided by n. So it's a free energy per particle, or free energy per spin. Okay. We have in total n spin in our system. We take the free energy of the whole system, we divide it by n. Okay. Now it doesn't matter if I'm looking on f or I'm looking on f divided by n, because I need to find the minima. So if you divide everything by a constant, it doesn't really matter. Okay. So when I take a log of this guy, so what I find f equals to, so it's just whatever stands in the exponent. I have 1/2 beta cancels this beta over here, j tilde m squared. So this is the first term. The second term, it is minus 1/2, oh I'm sorry, there's no 1/2, it's just minus 1 over beta log of 2. I separate 2 and the cosine. I have minus 1 over beta of a log of a hyperbolic cosine of beta mu h plus j tilde m, and I close all the parentheses. This is my free energy. Depends on the free parameter m, that I have no idea what it is. It also depends on the, somehow depends on the external field h. Okay. J tilde is kept constant, beta is 1 over k Boltzmann T, so G tilde I know, beta I know, I can control it, h I can vary, it's the external field that I applied, and the question is what is m? Okay. So the question is how it's solved. According to this prescription, we find a minimum. So we have df to dm equals 0. That's the equation. Now, what we want to find, we actually want to focus on the specific case when the external field H equals to 0. Right? Because the whole idea is if I have some external field, of course I'm going to get some non-zero magnetic moment. Why? Because the spin will prefer to go in the direction of an external field. But the whole, the interesting part is, well, can we have a magnetic moment that is not due to the interaction with the outside world, but to the inside interactions of the particles among themselves? Okay. So we're setting H to 0, and we want to explore this equation over here. Okay. So we don't have mu H over here, which is nice. And we take the derivative. Yes? No? No. Okay. So what's the derivative? So we have 0 equals 2. The derivative of this guy with respect to m is just j tilde m. The derivative of this guy with respect to m is 0. It's independent of m at all. And we have minus 1 over beta. Now derivative of whatever stands inside, so it's a log of whatever stands inside, so it's 1 over cos, hyperbolic cosine of, we forget about mu h, and we look only on beta j tilde m. Right, so it's beta j tilde m. Okay. And now we take the inner derivative, which is
Sine.
hyperbolic sine of beta j tilde m.
This is the, how do you call this?
This is a hyperbolic tangents, right? But we still have something else over here. What is the additional stuff that we have inside?
Beta j tilde.
Beta j tilde. Okay. So we cancel out these betas.
And you can also cancel out the j tilde.
I can also cancel the j tilde. Right. So let's write the equation. M equals to hyperbolic tangents of beta j tilde m, and that's it. Well, solve this, okay? Solve this guy, and we'll get m. So m is the specific something, specific variable that satisfies this equation. Now,
This is, but this equation is, איך אומרים סתום באנגלית?
closed form equation, and there is no clear solutions. Yes, but we can at least explore it. We can see what happens. So the question is m always equals to 0? Because if m always equals to 0, then we're stuck. Why? Because, well, we got that interactions are not important. If you don't have an external field, you will get always, on average, 0 magnetic moment. Now, this is the intuitive solution, right? If you think about it, I'm looking on all the different guys around myself. Some of them can be up, some of them can be down. There is no preference to pointing either up or pointing either down. Absolutely no preference. Okay? The only thing that happens is that, well, there are some sort of interactions, but they can be in that direction and that direction. So why should I get non-zero solution? The intuition says you shouldn't get. In experiment we see it. Okay? This is what Pierre Curie discovered. So let's try and explore it. How do you explore closed form equations where you don't have an explicit solution? Graphic solution, right. So first of all, this is m, and we plot the hyperbolic tangents. So the hyperbolic tangents looks something like this. This is the hyperbolic tangents of beta j tilde m. Now, when we plot m, it's just a straight line. Now, this straight line, okay, can have the following features. This straight line can be something like this. Okay, so first of all, when m equals 0, hyperbolic tangents equals 0. So there is always a solution when m equals 0. M equals 0, 0 equals hyperbolic tangents of beta j tilde multiplied by 0. So there is one crossing point, always. But you see, I somehow plotted the slopes arbitrarily. Okay? So the slope of m, this is m, is always 1. The slope of hyperbolic tangents, when m equals 0, it's actually not 1. It's something that depends on beta and j tilde. Okay? So what is the slope of this guy at 0? Let's take a derivative and calculate the slope at m equals 0. Okay? So we're doing d to dm of hyperbolic tangents of beta j tilde m, and we want to calculate the slope at m equals 0. Okay. What is the derivative of hyperbolic tangents? Do anybody remember? Let's derive it. Okay. So it is d to dm of hyperbolic sine of beta j m divided by hyperbolic cosine of beta j tilde m. Okay? So, so first of all, we take a derivative of hyperbolic sine, which is hyperbolic cosine of beta j tilde m multiplied by beta j tilde divided by hyperbolic cosine of beta j tilde m minus 1 over hyperbolic cosine of beta j tilde m to the second power multiplied by what? Hyperbolic sine of beta j tilde m multiplied by beta j tilde multiplied by hyperbolic sine of beta j tilde m. Okay, so in total we're getting 1 minus hyperbolic sine squared of beta j tilde m divided by hyperbolic cosine of beta j tilde m, all of this multiplied by beta j tilde. Cosine is squared, right? Cosine is squared. So what we have, it is hyperbolic cosine squared of beta j tilde m minus hyperbolic sine squared of beta j tilde m divided by hyperbolic cosine squared of beta j tilde m multiplied by beta j tilde. What is hyperbolic cosine squared minus hyperbolic sine squared? 1. You all knew this in high school. So it is beta j tilde divided by hyperbolic cosine squared of beta j tilde m. Now I want to compute it where m equals to 0. Hyperbolic cosine of 0 is 1. Okay? So all of this is beta j tilde. So while the slope of this guy is 1, the slope 1, the slope of the hyperbolic tangents is what? Slope beta j tilde.
So anytime beta j tilde is greater than 1, there will be more than 1.
Exactly. So let's plot it. Let's plot it. So the point is, if you look on the slope of the red guy, of the red curve, so when beta j tilde is sufficiently small, the slope here is less than 1, okay? The slope of the red curve is less than 1, then now you see the function is converging to a constant, so its slope is maximal at 0, and it's getting smaller and smaller and smaller and smaller. It approaches 0. Exactly at the same point, it's approaching 0. Okay, so the slope of the hyperbolic tangents is maximal at this point. So when the moment that the slope over here is less than 1, there is going to be only one single crossing point. Just one single crossing point between the m and the hyperbolic tangents. So what we know when beta j tilde is less than 1, only m equals 0 satisfies the equation. But what happens when beta j tilde is larger than 1?
Then not more than 1.
Ooh, there are more points, right?
Yes.
There are more points. So if you plot, this is m, this is hyperbolic tangents of beta m j tilde. We plot it like this. Okay. And when we plot our straight line, okay, we know that here beta j is larger than 1. So therefore the slope of the red guy, the red curve, is larger than the slope of the blue curve. So we're going to have two additional points. M0 and minus M0. And they're symmetric because the symmetry or anti-symmetry of the hyperbolic tangents.
So what happens when j tilde is equal to 1?
We'll get to this point. We'll get to this point in a second. Okay, so what this graphical solution suggests, okay? This graphical solution suggests the following thing. This is the equation that we explored. M equals hyperbolic tangents. Okay? So we know that for beta j tilde less than 1, there is only one point, only one. Only m equals 0 satisfies m equals hyperbolic tangents of beta j tilde n. What it means if I have one point, where this equation came from. So it means only single solution, only a single solution, single point that satisfies df dm equals 0. So it has to be a minimum, right? So it has to be a minimum. So what we see that for beta j tilde smaller than 1, beta j tilde smaller than 1, f has one single minimum. So if we plot f as a function of m, there has to be one single minimum at 0. Okay? So therefore, for beta j smaller than 1, okay, there is only one solution, and the magnetic moment has to be 0. This is paramagnet. Okay? But So basically, okay, if we write it down in what form? We write it down for temperature. So what is this condition? The condition is beta j tilde smaller than 1. Beta is 1 over k Boltzmann t j tilde smaller than 1, or t larger than j tilde divided by k Boltzmann. For any temperatures that are higher than j tilde divided by k Boltzmann, we have only paramagnetic behavior. Okay. Now, this is fine. This is dull and not interesting in a sense that yes, we expect paramagnetic behavior, but what happens in the other region? Okay. So for beta j tilde larger than 1, okay, 3 possible m satisfy df to dm equals 0. So we have to define what is the minima and what is the maxima, because you remember the crucial part, the physical point is find the minimal, global minimal, not a local minimal, the global minimal of f. Okay? So we need to understand what happens when this transition takes place. Maybe those additional 2 points, great, they solve this equation, m equals to hyperbolic tangents, right? But maybe those are no new minima, maybe they are maxima, right? So something else, we need to explore this guy. What happens over there? Okay, any suggestions? What should we do? Yes?
I think we know that in infinity, there couldn't be any minima to the equation.
In what do you mean in what infinity?
In infinity of m.
In infinity of m, okay.
So we should expect f to explode.
This is great, this is what happens.
This is what happened. We should also expect f to explode in those conditions.
Alright, fine.
Just
So-
plug it in here.
In this condition. So we assume that both m0 and minus m0 should be minimal their respective behavior.
Okay.
So the question is which is the larger minima, and f0 is the maxima between them.
Okay, so the claim is as follows. Let me interpret what you say. So what we know, if you look on f as a function of m, we know the following thing. M, okay, when m is extremely large or extremely small and negative, this is not a possible solution. Okay? This is not a possible solution. So f have to be large in these regions. Okay? Why it has to be large? Why it has to be explode? Because if it will go to minus infinity, which go to 0, it would be a minimal solution. So the claim is it has to explore. Now we have 3 possible solutions where the df to dm equals to 0. Okay? And your suggestion is that the function have to look like this.
Yeah, something like this.
Something like this. Okay? That this function have to look something like this. This is going to be minus m0. So this is going to be plus m0. Okay? And this is 0. And therefore, those 2 additional solutions, okay, therefore those 2 additional solutions are providing to us those new behavior, the non-zero magnetic moment. Okay. So let's see if this is true. Yes. F, it's your free function. You remember? F is the free energy divided by n. Is the free energy per particle. No, tangents, hyperbolic tangents we obtain from the equation df small f divided dm equals 0. Okay. Okay, so what I suggest is Great point. But what I suggest that we do, that we explore the behavior of M in the vicinity of 0. Okay? So let's explore the behavior of f of M in the vicinity of M equals 0. Okay. So we know something happens there. Why I suggest to go into 0? Because you see, if we plot the hyperbolic tangents, beta j tilde M as a function of M, okay, and I know when the slope here is close to 1 or a little bit higher than 1, okay, the crossing points between this slope and the straight lines are going to be also close to 0. Okay. What I'm saying is when I look on the two slopes, when the slopes are close to 1, also the M0 and minus M0 are also going to be close to 0. Okay, when the slopes are exactly the same, so there is only one crossing point, which is 0. When one slope, or the slope of the hyperbolic tangents, is smaller than 1, there is still one crossing point, exactly at 0. When it's larger, but a little bit, also the solutions are going to have to be close to 0. So everything, all this specific behavior, is it something like this or something else, is going to be described to me if I look on the vicinity of this function in the vicinity of 0. Okay? So I suggest that we explore our f in the vicinity of 0. Okay, so let's write down our f, and we still do not consider, and I don't think that we will have time to consider what happens to the external field. Okay, so what was f? F was 1/2 M j tilde
It's M
squared. M squared j tilde, not, that wasn't squared.
The M was squared, J tilde
Wasn't. Here I have minus 1 over beta log of 2. Right? What else did I have over there? What? Minus 1 over beta log of cosine or sine? Hyperbolic cosine of beta M j tilde, right? And that's it. This is what I had? Okay. Okay, so what we are going to do, this is f of m. We assume that m goes to 0. When m goes to 0, I'm going to expand those guys in the vicinity of this m goes to 0. Okay? So this is already an expansion, so this is m squared. So I don't really need to touch this term. Okay? This is an additional term which is constant. I'm not going to touch this term either. So the only thing that I need is to explore how log of, or 1 over beta minus of hyperbolic cosine of beta m j tilde, how it behaves in m goes to 0 limit. Okay? So I'm using a Taylor expansion. Fine? I'm using a Taylor expansion. Taylor expansion. Okay. I'm using a Taylor expansion of this guy. So first of all, we see if we get here m equals 0. So the first term is minus 1 over beta log of hyperbolic cosine of beta multiplied by 0 j tilde. Okay, so what is this? What is cosine of 0? It's 1, right? Hyperbolic cosine of 0, it's 1. Now, a logarithm of 1 is 0. So I don't have this term. Okay, so the 0 term is neglected. Okay. Then I'm taking the first derivative of this guy. So what was the first derivative? I have minus 1 over beta, right? And do you remember what I've got over here? The first derivative, it was hyperbolic tangents of beta m j tilde multiplied by beta m beta j tilde. Okay? And I multiply it by m. Now this guy I have to compute at m equals 0. What is the value of hyperbolic tangents squared? It's going to be squared. Okay. It's going to be 0. Okay? So when I substitute over here, it's hyperbolic sine divided by hyperbolic cosine. Hyperbolic cosine at 0 is 1. Hyperbolic sine at 0 is 0. So this guy also gets out. This equals to 0. Okay. Now, we're going to explore what happens to this behavior up to 4th order. So instead of me trying to describe to you, okay, what is going on over there, I will just write down what happens. So the second order will provide minus 1 over beta multiplied by 1/2 of beta squared j tilde squared m squared. The third term is going to cancel out, the third order, and we are going to explore up to the 4th order. Why not? I will explain in a second why. And it's minus 1 over 12 beta to the 4th j tilde to the 4th m to the 4th. Okay. So this is the expansion. Now you can ask me, Stas, why on earth you want to explore the behavior of this guy up to the 4th order? Okay? Why to the 4th order? So first of all, the first order is 0. The 0 order is 0. So I had to explore up to the 2nd order. But you see, we already have a 2nd order over here. Okay? So what terms we had in the first place in our behavior? We had 2nd order of m, 0 order of m. We can say, well, let's take just the 0 order. Okay? Let's just take the 0 order and get done with it. Okay? But it's not enough. And I will explain in a second why. We actually need some sort of an equation. Okay, so let's write down our f of m. F of m, it equals to 1/2 m squared j tilde minus 1 over beta log of 2, just a constant. It depends on the temperature, but it's a constant. We have minus 1/2 beta j tilde squared m squared, this guy, and we have plus 1 over 12 b to the 3rd j tilde to the 4th m to the 3rd. This is our f of n. Because I already done a calculation in my head. It's to the 4th. You're right. Thanks. Okay. So remember the points that we're interested in. First of all, this is expansion around m equals 0. The points we are interested in are such points where df to dm equals 0. And we expect that the solution to this equation should be somewhere in the vicinity of m equals 0, because this is what we've got from the graphic exploration beforehand. Okay? This is why we did the Taylor expansion, and we neglected everything what happens to the function away from 0. Okay. So we solve this guy. Okay? First of all, we want to see that indeed we'll get 3 solutions. Okay? So what the solution? Now it's easy. Why it's easy? It's a polynomial. Now let's take the derivative. So 0 on the left hand side. On the right hand side we have what? m 2 divided by 2 j tilde from this part. This is a constant with respect to m, so this is just 0. We have minus 0. What happens over here? We have minus 1/2 multiplied by 2 beta j tilde multiplied by m. Okay? And we have an additional guy, which is plus 4 divided by 12, so it's 1/3. Beta to the 3rd, j tilde to the 4th, m to the 3rd. Okay. So let's write it over here. So it is third order algebraic equation. Nothing fancy, right? So let's rewrite everything. So what we have m multiplied by j tilde minus, where was j tilde squared? Here's squared, so here's squared. Minus beta j tilde squared plus 1/3 of what? Of beta to the 3rd, j tilde to the 4th, and an additional solution is m to the 3rd equals to 0. M squared?
You took m outside of the
No, but I took outside m over here. So I had m to the 3rd is over here. Let's do as you say. Let's take m out, and what we have here is j tilde minus beta j tilde squared plus 1/3 beta to the 3rd j tilde to the 4th m squared, and all of this equals to 0. Okay. So obviously m equals 0 is the solution, right? So when m equals 0, 0 multiplied, nothing explodes over here, something equals to 0. Okay? So m always a solution. Now let's look inside. So we have j tilde minus beta j tilde squared plus 1/3 beta to the 3rd j tilde to the 4th m squared equals to 0. What happens to this guy? What can we say about him? It's always positive, right? For any temperature, for any beta, right? Temperature is positive, beta is positive, beta to the 3rd is positive. J tilde to the 4th, well, maybe we had negative j tilde, who knows, right? But j tilde to the 4th is positive, and m squared is always positive, or 0. So this guy, greater than 0, or equal to 0. Okay? What happens to this guy? So it is j tilde multiplied by 1 minus beta j tilde. So we have two solutions.
Yeah,
when beta j tilde is larger than 1, it is negative. Okay? On the other hand, when beta j tilde is smaller than 1, it's positive. But we had this condition about beta j tilde larger than 1 or smaller than 1, but this was with response to what? To the hyperbolic tangents. But we see here, there is some sort of additional, the same transition for this term, positive or negative. What do I care if it's positive or negative? So, because if this guy is positive, this is also always positive, it can never be 0. Okay? So, when this term is positive, the sum always positive and it cannot be 0. No additional solutions. No additional solutions to df dm equals 0 besides m equals 0, right? So when beta j tilde is smaller than 1, there is only one solution and it is m equals 0. What is beta j tilde? It is T larger than J tilde divided by K boson. Okay, so the high enough temperatures, there is only one solution. This is exactly what we got before. So this is good. On the other hand, when beta J tilde is larger than 1, this guy is negative. Additional solutions. Okay, so we have a consistency between the hyperbolic tangents description and whatever we derived by using the Taylor expansion. We have exactly the same criteria. Something happens for T equals to J tilde divided by K boson. Okay? So first of all, let's find what are those solutions. The additional solutions.
סטאס, יש לך שאלה?
Yes.
למה אתה אומר ש-J tilde יכול להיות כאילו J tilde הוא שלילי ואז J tilde כפול 1?
No. J tilde cannot be negative. J tilde cannot be negative. It's a positive something. It's a positive coupling constant. Okay? If you remember how we defined the coupling constant, J tilde has to be negative in order for when the spins are aligned, that the total energy would be negative. So it's a more probable state. That's it. J tilde is negative. Sorry, positive. Okay?
תודה.
סטאס,
Yes.
אתה יכול לענות לה בעברית.
Okay. אני בשוונג כבר. All right. The last part. Let's solve this. So we assume that beta J tilde is larger than 1. Okay? Therefore, 1/3 beta to the 3rd J tilde to the 4th and to the 2nd equals to beta J tilde minus 1 multiplied by J tilde, or n to the 3rd equals to beta J tilde minus 1 J tilde divided by 3 beta to the 3rd J tilde to the 4th, and we have two solutions. M0 plus minus equals to plus minus a square root of 3 beta J tilde minus 1 J tilde divided by beta to the 3rd J tilde to the 4th. So we don't need, at least in the vicinity of m equals 0, we don't need to solve this hyperbolic tangent somehow graphically. We can do this, expand in the Taylor series, obtain the two solutions. But still the question remains, what is those? The minimal, the maximal, what are they? Okay? But now we can plot, right? So we can take this guy, okay? We can take this guy and we plot it and just check what is a minimum, what is a maximum. Well, of course we can do another series of derivatives and then check, but it's easier to plot it right now. So this is what we have.
First of all, we can say that the two solutions are having the same value.
This is great, right? Well, what's the problem? One is negative, one is positive, so what you're saying is consistent with whatever we had from the graphical solution. I agree. Okay.
Because it's an even function.
Yeah, no? Yeah. So what we have three regions. First of all, this region when t larger than j tilde divided by k Boltzmann. Okay. So this is f, this is m, and we have t larger than j tilde divided by k Boltzmann. So what happens? For m equals 0, it equals to minus 1 over beta log of 2. So it is, and it's an even function, so it goes like this. There is only one single minima. Okay? Only one single minima. And the system sits in this one single minima, and nothing happens, so the magnetic moment equals exactly to 0. We increase the temperature, till we hit this point when T becomes J tilde divided by K Boltzmann. Okay, so what happens exactly at this point? Okay, so we go and we plot this function again. M, this is F, this is T equals to J tilde divided by K Boltzmann. So what happens over here? This one single minima, okay, what will happen is it's becoming broader. In what sense? That we have something that looks very flat. So not flat as m squared, it's actually going to be flat as m to the 4th. Okay? So it's still one flat function. Okay? So exactly at t equals j tilde divided by k Boltzmann, we have only one solution. Okay? Only one solution, and this is m equals 0. Okay? Now we go even further to lower temperatures. And you can shift your temperature slightly by delta from this T equals J tilde equals J tilde by K Boltzmann. So this one single minima over here is going to split. Okay? So it's becoming flatter and flatter and flatter. So think about it. It's a minima, and the minima becoming flatter and flatter and flatter. At some point, the minima will transform into a maxima. Okay? So this minimal guy over here will transform into a maxima. And two minima will split. M0 minus M0. Okay? So what actually happens over here is that we had one single solution. And there was absolutely nothing bad to this one solution. But as we lowered the temperature, the free energy was modified, and it was modified. And specifically, it was modified around this minimum, around the global minimum of the whole system. Okay? And this minimum became extremely flat, okay, at some critical temperature. This is our TC. And as we lowered our temperature even lower, this minima, it's not a minima anymore. It's a maxima. The system has to sit at a global minimum of the system. So it can go either over here, or it can go either over here. Okay. Now, what happens if we plot all of our solution over here as a function of temperature? If we plot them as a function of temperature, so this is T, this is M, the average value of the spin. So here we have Tc, which is equal to J tilde divided by K Boltzmann. So we know it is 0 for large temperatures. Why? Because have only one single solution, one single minimum. The moment that we cross exactly at Tc, we still have only one solution. But the moment that we cross this Rubicon, okay, this value of m equals 0, it's not a stable point anymore. The stable points, the minimum of the systems are m0 and minus m0. How they behave? Like this. Okay? And when you plot those m0s, because the solutions are m0s, you have one positive and one negative. So one will go like this, and one will go like that. Okay? One will give us a positive moment. The other one will give us a negative moment. Now, if you explore this equation over here, you will see that it goes as square root of T minus Tc. I'm sorry, let's write it square root of Tc minus T.
The vicinity of Tc?
Minus square root of Tc minus T. Where it's come from? Expand this guy. So you have a square root, and here beta j tilde minus 1. So if we look on square root of beta j tilde minus 1, it will give us a square root of Tc minus T. Because I know that Tc equals to J tilde divided by K Boltzmann. Two solutions. Not trivial solutions. So in nonlinear systems, it's called a bifurcation fork. Right? So we had one solution, because we're watching on the global minima or free energy. We reached a Rubicon to which this one solution, something bad happens to it, and it splits into two different solutions. Okay? So the system or the interactions become extremely important in the vicinity of this point. Okay? Extremely important. And by the way, this those exponents also can be exactly this behavior. This is what people see in experiments. Okay? So the system is not going to be now in the trivial position, m equals 0. This is actually not stable. Interactions modify the stability of the system, self-interaction. You can say, well, but there were exactly the self-interactions beforehand. What are the interactions? J, the coupling constant, Si multiplied by Sj, are the same interactions. But no, temperature, it's an important part of it. So the moment your temperature is high enough, the interactions are less important. If you remember, it's always e to the power minus beta multiplied by the energy. Okay? So if we have large temperature, the interactions are not important. But when you have small temperature, the interactions become super important, and what they cause the global solution to go from minima. They actually turn this point of symmetry to be non-stable, and the system goes either to the minus m0 or either to the plus m0. Yes? Great question. So all of this happens when we have absolutely no external field. Absolutely no external field. This is the point. If you have an external field, you don't care about the transition or the self-induced momentic moment, because you have interactions with the external field, and the external field can induce this moment. Here, happens It happens for what? For a zero external field. But this brings me to the next point. So usually I don't have a lot of time to explore it, but look on this behavior. So all those three plots over here were for h equals 0. Okay. So whatever we plotted over here was for h equals 0. What will happen if I introduce non-zero h? I can perform exactly the same thing that I've done in the last hour or so. Okay, this is why I don't have time. But if I would have additional time, what would I get for the free energy when h is larger than 0? Okay. So when h is larger than 0, I would get the following thing. So for high enough temperatures, this is F, I will have a minima, but not at 0, right? Because I have an external field, and this external field will say, well, yeah, you will have some non-zero self-moment. Why? Because you're interacting with the external field. So the free energy will look like this. Okay. So what we have a shifted minima. Instead of getting a minima at 0, we're getting a minima at some specific m1. Why? Because we have interactions with the external field. Okay. Great. What will happen next? As I decreasing the temperature, I will see something peculiar happens to my free energy. So here, this guy was getting fatter and fatter. Okay, so it's just flatter and flatter. Now, as I increase my temperature, F will start to develop an additional dip. It will look like this, and I increase I decrease my temperature. I'm sorry, even more, and this is F. This is M. This is M. This is M. And at some point, this guy will become like this. And my system is still sitting in this global minima. Okay. Because h is non-zero anymore. Because there are interactions. You see, the second dip, where it comes from an interactions between the moments. And the moment, the spins, and the moment the spins can reorganize and create another situation. It's going to be metastable state, because the system will still prefer to sit over here. Okay? So for low enough temperatures, you have two preferable stable states. One is the global minima. The system will eventually sit over here. But the other one, it's not a global minima. Okay? But still a minima. Now, what will happen if I will now reverse? So this is h larger than 0. Exactly. But not due to the temperature. It depends on the strength of the temperature and the external field. But if I'll take this situation, okay? If I'll take this situation and I'll say, let's go and now shift h. Okay. So I know when I'm reaching at h equals 0, I will get, if I'm below TC, I will get to those two solutions. Okay? This is F, this is M. I will get to here. And the system, because it was sitting over here, it still sits over there. I will shift my H to a negative position, a negative values. What I'll get, this is F, this is F, this is M. I'll get that this peak will become smaller. Okay. And the system will prefer to get over here. Okay. So for H, the behavior is quite different, right? Because the position of the minimas are different. And the behaviors of the minimas are different. Okay? So it's different from the behavior of H equals 0. When H equals 0, we just explore this function. And what happens to this function is those two minima and the maxima collapses to one solution, and there is only one global minimum. When H is non-zero, I can have additional dips. But those dips are usually going to be metastable. But there is a transition from this guy to that guy, which is more peculiar. There was a question, yes?
So the positive M solution stays about the same?
They will depend on H, linearly.
So H will actually flip the plot. Okay.
So if you remember the hysteresis loop, you remember the hysteresis loop? So the hysteresis loop comes from what? Comes from the system, even when H gets to 0, and I expect the system to go where? To the position where M is 0, the system is going to sit over here. Okay? So this is why I have in the hysteresis loop non-zero moment even when I shift my external magnetic field to 0. Why? Because in the free energy there are two dips, they're exactly the same, but the system was sitting on the right hand side, so it will be still sitting on the right hand side. It's only when I'm getting the H towards the negative value, this guy will overcome that guy, and the system will go to a negative magnetic moment. Okay, this is the explanation of the hysteresis loop. Now, the last thing, and I don't really have time, is actually all of this. This is the starting point of something that's called Ginzburg-Landau theory of phase transitions. And I need 3 additional hours, and I don't have them, so I will just explain, just give you a prelude of what's going on. So, look what happens over here. I had one solution. I had a paramagnetic state. I had a paramagnetic state. I had a paramagnetic state. And then there was no jump. Nothing really happens. This paramagnetic state splitted into 2 states. And I had a continuous transition from paramagnetism into ferromagnetism. Okay? This is a phase transition. And in this phase transition, my magnetic moment continuously shifted from 0 to a non-zero solution. So this is a continuous phase transition. Continuous phase transition. What is order of a continuous phase transition when nothing jumps?
Second.
It's a second order. Okay? So for second order transition, what we'll expect is a splitting of 1 minima into 2 maxima. So this is second order phase transition. Second order phase transition. What happens over here? We had one solution. It was a positive solution. It was a positive solution. It was a positive solution. And I shifted my H too far. And instead of sitting here, the whole system will jump from this point into that point. Okay? I will observe a finite jump of my magnetic moment. So it is a not continuous transition. So think about it. I had positive magnetic moment, positive magnetic moment, positive magnetic moment, positive magnetic moment. I shift my external field a little bit too much, negative magnetic moment. The system will explore a finite jump from positive magnetism to negative magnetism. So it's a phase transition of which order?
First.
It's a first order phase transition. First order phase transition. At this point, what led Landau and Ginzburg to develop their theory of phase transitions, because you see the whole idea is to explore the free energy. Okay? The moment that I know what is free energy, the moment that I know how the minima of these free energy behaving, I can explain everything about phase transitions. When I have a finite shift from a single maxima to another single maxima, it's a first order phase transition. When I have a continuous transition or splitting of one single minima into two additional minima, I'll have a second order phase transition. So the only thing that I need to explore in order to understand the behavior of phase transitions is give me the free energy, how it behaves as a function of some order parameter, explore it, and you will know everything. We will stop here. I won't explain to you additional stuff about free energy. We ran a little bit at the end, but that's it for the class. I hope you enjoyed it, and I'll see you all in the exam. Thank you.
סטאס, אפשר שאלה?
כן.
בתחילת השיעור היה את החלק עם האנרגיה הקבועה, נכון?
כן.
שהיה את הבטא JM, משהו בסגנון הזה עם
כן,
חלקי?
כן.
אז תאורטית, תמיד אנחנו אומרים שאנחנו יכולים להגדיר את האנרגיה ביחס לקבוע, אז כאילו למה לא היינו יכולים להוריד את זה?
כי הקבוע הזה הוא לא ידוע, הוא תלוי ב-M, נכון? ברגע שאני לא יודע מה זה M, אני לא יכול בדיוק להוריד אותו.